Hello and welcome to this video covering the most common styles of exam question within the proteins and enzymes topics. We will look at questions on protein structure, enzyme action and practical applications of your knowledge in both of these areas. To get the most out of this video, I would suggest completing the proteins and enzymes exam style question worksheet in advance. So question number 1 gives you a diagram of a chain of amino acids and it asks you to draw rings around the R groups in the diagram. Now I'm hoping you'll be able to spot that this is a tripeptide, and you can see that because there are 3 nitrogen atoms within the molecule. It hasn't actually shown you the carbon atoms within the backbone of this molecule, but you can imagine where they would be. And we are looking for the R group, so we need to spot our 3 separate amino acids and we need to look for the central carbon within each of those amino acids and look for the R group coming off. Now we know that each of our amino acids will have a hydrogen coming off that second carbon atom, and then additionally its R group. The first amino acid actually just has 2 hydrogens. It doesn't matter which one you circle. I'm going to circle this one on the bottom. In the second amino acid we have a CH3 group coming off, so I'll circle that one. And then for our third amino acid, we do have a slightly funny arrangement here, but you just need to look for what you know. So we know that there must be a carboxyl group at the end of our tripeptide. So we know that that isn't the R group. So we look for our middle carbon and we look for what's coming off that. And we've actually got 2 hydrogens coming off an additional carbon, so CH2 plus SH. And that is our final R group. So there I've circled round our 3 different R groups within that tripeptide molecule. So the second part of this question asks you to describe the formation of bonds between the amino acids, and there are 3 points on this mark scheme. So the first one is condensation reactions, and any time you are talking about building up reactions, building larger molecules from smaller molecules, you really do need to be referring to that phrase condensation reactions. The second marking point is for talking about the peptide bonds that are formed, and because it was a tripeptide, you really ought to be saying that there are 3 peptide bonds formed. And the third part is for saying that those bonds are formed between an amine group of one amino acid and the carboxyl group of the adjacent amino acid. And then the last part of this question asks you to state 2 structures that all amino acids have in common. I've shown you here a diagram representing an amino acid. And there are only 2 points on the mark scheme, so an amine group and a carboxyl group. You might see these described other places as an amino group and a carboxylic acid group, but because amine and carboxyl are on the specification, I would suggest that you use these terms amine and carboxyl. And then you might also think about writing that all amino acids have an R group. Now that is true, and you might even see it on some mark schemes, but if this was a 2-mark question, I would go for these points as your safest points because the R group can be variable. So you might actually put that as a difference that amino acids have different R groups. So the safest 2 points here would be to write about the amine group and the carboxyl group. So the second question is a slightly longer answer question asking you to describe how changing one amino acid within a polypeptide chain could affect the structure of a protein. And it is specifically referring here to hemoglobin as our protein. So I've put an image here to show you the structure of hemoglobin. So it's composed of 4 different polypeptide chains, 2 alpha and 2 beta, and the little green parts that you can see are the heme group with the iron, and that is where the oxygen binds. Now, if you didn't know the structure of hemoglobin, there is a bit of a clue in the question. So it talks about hemoglobin's polypeptide chains, plural. So it does give you that little bit of a clue that here we have a protein that has a quaternary structure, which is all you really need to know to answer this question. So if we start at the beginning on the mark scheme, if you change one of your amino acids, you alter your primary structure of your protein, which means you change your sequence of amino acids. And that in turn would alter your tertiary structure because that is due to the bonds that form between the R groups. And those bonds, if they form in slightly different ways, would alter the way that the protein or the polypeptide folds up into a specific 3D shape. You do need to give some examples of those bonds. So they could be hydrogen bonds, disulfide bridges or ionic bonds. And it is definitely good practice to put all 3 into your answer. You could also affect any hydrophilic, hydrophobic interactions that might take place within the polypeptide or the protein. And that's to do with the polar and non-polar R groups. And they affect how the overall structure folds up to create a 3D structure. And for example, if we think about hemoglobin being a globular protein, we would expect that around the outside of that molecule, you would have polar R groups, and that enables that molecule to be soluble in a watery environment like the blood. And then finally, because we know that hemoglobin has a quaternary structure, if a bond that is affected happens to be one of the bonds between the polypeptide chains, then we could also alter our quaternary structure. So question 3 is an amino acid chromatography question. Now this is not directly on the syllabus, but it is stated as an opportunity for skills development within the specification, so it is worth being familiar with. I've also seen this come up on AS exam questions in the past. It could either come up as with an electrical current applied, which is different to this question, or a simple chromatography as we have in this question. It's also, chromatography is in the A2 syllabus as part of the photosynthesis topic, so it's definitely worth being familiar with chromatography and amino acid chromatography at this stage. So I will start by just talking you through the process of what the student did in her experiment. So she had her mixture of amino acids, she had 4 different amino acids, and she applied them to the bottom of her chromatography paper, just slightly off the bottom. And you would add a drop of your amino acid mixture, let it dry, add another drop, let it dry a few times just to increase the concentration of your amino acids. And you would then dip the bottom of your paper into the solvent. It's really important that it's just the base and that you don't submerge that application point. And then you would allow the solvent to move up through the application point and to carry any dissolved amino acids with it as it moves up through the paper. And then if we have a look at what she found at the end of her experiment, so she allowed the solvent to move, you would stop it before that solvent front falls off the end of the piece of paper. And that because that solvent front is quite important, particularly when you look at things like RF values, when you do this next year with photosynthesis pigments, that position of that solvent front is important. So you'd always stop it before the solvent falls off the end of the paper. And she also had to spray, she had to dry it off at the end and then spray it with anhydrin to actually show up these spots of your amino acids. And she saw some different dots, and we need to think about why the different amino acids might have moved different distances. And that is affected by a couple of different factors. So one of those is that the amino acids are differently soluble in the solvent, and it is specific to the particular solvent that was being used in this experiment, but they have different solubility in that solvent, and therefore they'll move different distances along the paper in a set period of time. Additionally, the attraction to the chromatography paper might be different, and that can be affected by things like charge and mass, and that also affects how quickly the amino acids move and therefore the distance moved in a set period of time. So if we have a little look at the mark scheme, we've got different amino acids move different distances due to the differences in their solubility, and you can talk about the solubility in the solvent or the mobile phase, which is another way of explaining the movement within the solvent. And then we have our distances also affected by differences in charge and mass. And as we said, that can affect the attraction to the chromatography paper, which additionally affects how rapidly the amino acids move. And then the last part of the question is for you to notice that there are only 3 spots, whereas we added 4 amino acids from our mixture. So why have we only got 3 spots? The most logical explanation for that is that 2 of the amino acids moved exactly the same distance, and you need to fully explain that. So the reason they might have moved the same distance would be they, for example, had the same solubility or charge or mass. So the second part of this question asks you to suggest an explanation for why the student needed to use an anhydrin solution. And it's a suggest question, and that means that you may not be able to get the answer from your syllabus content, but you should be able to work out the answer. And in this case, they've given you quite a lot of clues in the question. They've talked about an anhydrin being added and then the dots turning purple. So it's basically we're trying to visualise our dots because they were colourless before. And there's 2 marks on this because it said explanation. Whenever there's an explanation or explain in the question, that means you really need to explain fully. So here we've got amino acids are colourless, so we need to make them visible. So this could be a 1 mark question or possibly a 2 if they're being generous, but you do need that full explanation. And then for part C, it says how the student could determine the specific names of the amino acids in her mixture. And here you need to compare against the distances moved for known standard solutions. So this is the idea of comparing against something that you know. So taking a range of amino acids, seeing how far they move in a particular time, and then comparing it. Now, you could talk about RF values here, but it's not on the syllabus at AS, so you wouldn't be expected to recall this information. But because you might be familiar with this from A2 content, it's worth just having a little look at it now. So your RF value is the distance moved by your molecule divided by the distance moved by your solvent front. And what that value does is it standardizes that comparison. So it doesn't matter how long you've left it for, how far your solvent front has moved, because you're doing that ratio of the distance moved by the molecule divided by the solvent front, it means that you can easily compare between different experimental setups. And you can get the RF values for a particular solvent for any particular amino acid, and then you can compare them to the results in your experiment, and therefore you could name those particular amino acids. So the fourth question is an enzyme question, and this one asks you to describe the induced fit theory of enzyme action and to explain how this would enable an enzyme to catalyse a hydrolysis reaction. So I'm going to go through the mark scheme, and as we go through, we'll just pick up on some of those points within the question. So firstly, you need to talk about an enzyme substrate complex forming, and that is a really common theme within enzyme questions, that phrase comes up. So it's always worth considering, is that a phrase that might be relevant to my answer if it's an enzyme question? And then the enzyme and substrate interacting causes the active site of the enzyme to change shape ever so slightly to become truly complementary to the substrate. And it's really important that you get that idea into your answer of it becoming truly complementary. And then the active site changing shape causes the bonds within the substrate to just be stressed and to distort, and therefore to be more likely to break. And that reduces your activation energy. Now, I've talked about bonds breaking rather than forming because in the question it was asking about a hydrolysis reaction rather than condensation. And the other thing to point out about this question is because it's got an explain command term in there, generally with explain questions, you do need to access all marking points on the mark scheme to get your full marks. So if it is an explain question, you do need to be thinking about, have I put enough detail into my answer to access potentially all the marks on the mark scheme? So question number 5 is based on the enzyme required practical, and this one is using hydrogen peroxide and catalase, and the source of catalase here is potato. There are various different natural sources of catalase, such as liver is a really good one, but potato is another. And then you're given an equipment list here, and you're also given a method. And essentially the student is combining hydrogen peroxide with potato as her source of catalase, and in that reaction you get water and you also get oxygen, so you would get either some bubbling and you also get a gas given off, and the student is collecting their gas into a gas syringe in order to be able to calculate a rate of reaction. And initially they're just using pH 7 buffer solution, but then later in the experiment they compare with different buffer solutions to compare the rates of reactions at different pH values. So if we have a look at the data, so you're given the graph of her data, and the first part of the question is to calculate the rate of reaction between 0 and 10 seconds. And the reason we're interested in that first part of the graph is because that is the initial rate of reaction, and that's what we want to compare between our different pH values. And it's really important because you don't want to look at the part of the graph later on where things are slowing down. You want to be able to compare the fastest rate of reaction for all of your different pH values. So that's the bit that she's interested in. And we need to calculate our rate of reaction. So I've just added a curve to the graph. And then the equation that you're interested in here is change in y over change in x. And any rate calculation, what you're looking for is the change in something over time. And it's always worth drawing your triangle on your graph. So because this is actually a very straight line, this is quite a straightforward one. So we don't have to do too much sort of estimation here. We can actually work out what it is. But I have still drawn the line on my graph and I've drawn my little triangle, and I would always recommend that you do that. It also shows the examiner where your data has come from. And then we just need to calculate the change in y, which is the volume of oxygen. So that's 45 centimetres cubed of oxygen over 10 seconds. So 45 centimetres cubed of oxygen was produced in 10 seconds. And if we do the calculation, we get 4.5 centimetres cubed per second. Now there are 2 marking points here. The first marking point is for showing that you have done that correct equation. So you have done change in volume of oxygen over change in time. So for showing your full working. And the second marking point is for giving your answer, definitely remembering to include the units, which are centimetres cubed per second. So just a final reminder, really, really important in any calculation question that you include your full working, because even if you get your answer wrong, that means that you can still get marks if you've shown your full correct working. And I also just wanted to point out that you could be asked in an exam to draw a tangent on your graph. For example, you could be asked to estimate the rate of reaction at 15 seconds. And if you were asked to do that, you would draw your tangent to estimate the rate of reaction at that point. And then you would go for the same equation, doing change in volume of oxygen over change in time. I've done it here, roughly 2.9 centimetres cubed per second for 15 seconds. And just to be aware, that's another skill that they could ask you to do in an exam. So the second part of this question asks you to explain what is happening between 45 and 60 seconds on the graph. So I've circled that part of the graph for you, and essentially it's levelled off, and that's because nothing is happening. So no reaction, the reaction has ended. It is worth just pointing out that this is a time graph, and therefore if it levels off, that means nothing's happening. If this was a rate graph, if we had something like substrate concentration along the bottom and then we had rate up the side, if that graph levels off, it means you've reached a constant rate of reaction. So it might be, say, a constant maximum rate of reaction. So it's always worth just being really careful before you jump into your answer to check what's on the axis. But in this one, nothing's happening, the reaction has ended. Because it's a 2-mark question, we need to explain in a little bit more detail. And the reason reaction has ended is because all of the substrate has been hydrolyzed, and it's really important that you use that word, all of that substrate has been hydrolyzed. Part C, the student has now done all of her pH values, and she has starting to compare her different rates of reactions for those pH values, and she has stated that the optimum pH for catalase is pH 7, because that's when she got her fastest rate of reaction. And the question asks you to describe how that student could amend their practical method to obtain a more accurate estimate of that pH value. Now, accurate here, we're talking about how close that value is to the true value. And this is quite a common question style. Essentially what we need to do is use smaller pH intervals, because how do you know that it's actually pH 7 and not 6.8 or 7.2? So to obtain a more accurate value that's closer to that true value, you just need to use a range of smaller pH intervals between 6 and 8. Part D asks you to explain why the rate of reaction was 0 at pH 5. And the key thing that's happened here is that our enzyme has denatured, and that's happened because we've gone away from our optimum pH towards a more extreme acidic pH. That means we've got more hydrogen ions floating around, and that's going to interfere particularly with hydrogen bonds and ionic bonds. And if you imagine for an ionic bond, if you've got opposite charges attracted to each other, if you then suddenly got more hydrogen ions interfering, that's going to potentially break those bonds. If those bonds break, that will affect your tertiary structure, and a change in your tertiary structure, particularly in the shape of the active site, will mean that the enzyme substrate complexes cannot form. And that phrase is a really crucial one, and it's a really common one that comes up in all sorts of enzyme questions. So it's always worth seeing, could you put that into your answer? And then the last part of this question, state 2 variables that the student should have kept constant that are not already outlined in her method. Really important thing in here is to check the method and what's already in there. And you're looking for things like temperature, pH, enzyme concentration and volume, and substrate concentration and volume. The pH is already being controlled, and the substrate volume and concentration has already been clearly controlled. What hasn't been controlled is the enzyme in the form of the potato. And also the other one that should jump out to you is the temperature. So I've written here temperature of the solutions in the conical flask. I've explained that clearly because examiners can be quite picky about what exact temperature are you controlling. So do try and explain that fully. And then in terms of the actual enzyme, it's the potato that's acting as the enzyme in this case. But she's just said potato cylinders. She needs to give much more information about that. So you could write about mass, or you could write about length and diameter of the potato. So give specifics about the dimensions of the potato. Definitely don't write about size or shape, as they're often rejected on mark schemes. You could write about something like variety or type of potato, but safest would be to go for mass or length and diameter. So that's the end of this exam style question video in which we've covered the most common question styles within the proteins and enzymes topics. In the next series of videos, we will have a look at the structure of nucleic acids and then move on to DNA replication.